Right, so this is a video which looks at reversible reactions and equilibria and industrial processes which relate to reversible reactions. And these questions are taken from old IGCSE chemistry papers going back before 2009, but they're still suitable for use now. Now, this question obviously is looking at the production of sulfuric acid. Now, sulfuric acid has the formula H2SO4, and you should know that formula off the top of your head before the exam. And there are 4 stages in the production of producing sulfuric acid, and in the first stage, which is what this question is asking about, is what actually goes into this process. And in the first stage, you take sulfur, which is mined, and react it with oxygen, and you form sulfur dioxide. So the raw materials for that process are sulfur itself and, well, you might think oxygen is the raw material, but actually we wouldn't use oxygen, we'd actually just use air. So those are the raw materials, and they're heated together to form sulfur dioxide, okay. And in the second stage of the process, the sulfur dioxide is reacted with more oxygen to produce, in a reversible reaction, sulfur trioxide. And if we balance that there, we have 2 of those. So the next one is more air and sulfur dioxide are then heated and passed over the catalyst, and hopefully you should know what the catalyst is. It's V2O5, vanadium pentoxide, and this reaction here produces SO3, sulfur trioxide. And you should also know the conditions for that reaction, which are roughly about 450 degrees C and 2 atmospheres pressure. And you should also know what we actually use sulfuric acid for. Well, a huge amount of use is it's used as a fertilizer, and it's also used as to make detergents. Okay, when I say it's used as a fertilizer, it isn't used as a fertilizer. It's used to make fertilizers. Okay, and detergents. It's also in car batteries. So there are 3 uses there. Now, here's a reaction that you may never have seen before. We're taking ethene, which is an alkene, so it contains a carbon-carbon double bond, and reacting it with oxygen to produce this chemical here. And we're told that the delta H for this reaction is minus 214. So, this symbol here means that it's a reversible reaction. And delta H actually stands for enthalpy, change. Enthalpy being a posh chemist's word for heat energy. Now we're told that the delta H is minus 214, and what that's telling you in the question is that the forward reaction is exothermic, which means the backwards reaction must be endothermic. So the next question asks us what would happen to the amount of product formed if we change the conditions. So, if in a irreversible reaction we increase the pressure, the equilibrium moves to where there are less gaseous molecules. So let's have a look at the equation they've asked us about. Well, on the left-hand side of this equation, we've got 2 ethenes and 1 oxygen, so we've got 3 gaseous molecules. On the right-hand side of the equation, we've only got 2 gaseous molecules. So if we increase the pressure, we move to where there are less gaseous molecules, and that is the right. Okay, so all the questions asked us to do is predict what would happen. Okay, so we get more product because there are less gaseous molecules on the right-hand side. Now, if we increase the temperature, the equilibrium will always move in the endothermic direction. So we need to work out which is the endothermic direction, and we actually already have. Okay, I did it a moment ago. We actually said the backwards reaction was endothermic, because we said the forwards reaction was exothermic because of that minus sign there. So if the temperature is increased, we get less product, because the backwards reaction is endothermic. Now this question initially looks quite tricky, but actually they've given a huge amount of information in the question, so a lot of the marks can be picked up from reading the question. I'm just going to move this up a little bit so I've got more space to write the final answer. So we're asked about the raw materials from which nitrogen is obtained. Well, air contains 79%, 78% nitrogen. So we use the air to get the nitrogen for ammonia, which is NH3. And where do we get the hydrogen for NH3 from? Well, it's made by a reaction of water with natural gas. So the two raw materials are actually water and natural gas. So we then combine nitrogen with hydrogen to produce our ammonia. Now it will be a mixture because the production of ammonia is actually a reversible reaction. You have N2, 3H2, and all this you should know off the top of your heads really, producing 2 NH3. And you're expected to know the conditions, so we use 450 degrees C, 200 atmospheres, and a catalyst. And the catalyst we use is iron. Okay, now I'm afraid you just have to learn those conditions. There is a bit of leeway in terms of the temperature and the pressure because it varies in textbooks, but you definitely need to know that it's an iron catalyst. I should have really written catalyst after how slack. So at this point here we have something called a separator. So into the separator go the mixture of nitrogen, hydrogen and ammonia. And we need to obviously separate out the unreacted reactants from our product. So what we do in there is we cool the mixture down. Okay, and as it cools, the ammonia turns from a gas to a liquid. So the ammonia turns into a liquid, so the gases can be separated off and the liquid can be tapped off, and that's the ammonia. So how is ammonia separated from the unreacted nitrogen and hydrogen? Cool the mixture, NH3 condenses, turns back into a liquid, or it turns into a liquid. And what's done with the unreacted nitrogen and hydrogen? Well, having spent so much time getting the nitrogen out of the air and the hydrogen out of water and natural gas, it would be a shame to just waste it. So we actually just recycle it. So it's fed back into the reactor. So it's recycled. Now I was once told that 5% of the world's energy use went on making ammonia. And the reason that so much energy goes into making ammonia is because it can be used to make fertilizers. And here we have a question where they give you quite a bit of information. So they ask you about ammonium nitrate, and it's made by reacting ammonia with nitric acid. Now, you should know that ammonia is NH3, and you have to know that nitric acid has the formula HNO3. And they react together to produce ammonium nitrate. Now, ammonium is NH4. And it has a valency of 1. Nitrate also has a valency of 1, so ammonium nitrate is NH4NO3. And we can check the balancing there. 1 nitrogen, 3, 4 hydrogens, nitrogens over there. Oh, in fact, that was a right mess of balancing it. 2 nitrogens, 4 hydrogens, 3 oxygens, and we're done. Okay, another question on reversible reactions. This time, again, using a reaction you may not have seen, where we convert nitrogen dioxide into N2O4. And I'm just, again, going to move it up so there's a bit more space to write. So, how can you tell from the equation this reaction is reversible? Well, we've clearly got a reversible reaction sign there, and it's been stated that we have a dynamic equilibrium. So you should know the definition of dynamic equilibrium, and there are three things you should really mention: that the rate of the forwards reaction is the same as the rate of the backwards reaction. And this means that the amount of product and reactant does not change. They're not equal, but the amounts don't change. And this only happens provided you've got a closed system. So in other words, if you've got the same amount of substance in there to start with, you're not releasing anything, you're not adding anything to it. And what happens to the amount of product when the pressure is increased? Now, we said on the last slide that if we increase the pressure in a system, it moves to where there are less gaseous molecules. And in this system, we have 2 on the left and 1 on the right. So, because there is less on the right, we move to the right. So we get more N2O4. And if the temperature is increased, just like the last question we did, it moves in the endothermic direction. Now, which is the endothermic direction? Well, the minus sign here tells us that the forwards reaction is in fact exo. Okay, which means the backwards reaction must be endo. So that means we get less N2O4. And it's just coincidence that that's a similar thing. And the final question is, why is it important that oxides of nitrogen are not allowed to escape into the environment? Well, oxides of non-metals are acidic. Okay, so it's not very good to be releasing acidic gases into the atmosphere. They can lead to acid rain, and they could lead to breathing difficulties for people. Okay, so it's a very bad idea to be releasing oxides of nitrogen into the environment. Now, this is a tricky one marker. It was right at the start of an exam paper, and it said the decomposition of ammonium chloride is reversible. So you've got 2 colourless gases, ammonia and hydrogen chloride, and they form when ammonium chloride decomposes. And you might be thinking, well, how do I force it in the forward direction? You're thinking, well, they've not told us anything about the enthalpy change here. Normally you'd expect a delta H sign there, so you might know whether to cool it down or heat it up. But the clue is actually in the top bit of the question, the decomposition. Now, if it's a decomposition, usually you need energy to make it go. Okay, so this is in fact an example of a thermal decomposition. So you heat it